So I tried for a while to think of a clever talk title for this. I did, because I gave a SigMF talk in 2017. I don't know, I probably spent 30 minutes trying different titles, and I just gave up. So now it's a statement. It's SigMF, period. So the point of this talk is to give a brief intro to what SigMF is for those who are unaware of it. And even if you do know what it is, to perhaps give a little bit more insight into what the original design goals for it were, which might perhaps explain some of the design decisions that we've made. Talk about its current state and where we're headed. So SigMF came out of the DARPA SDR Hackfest in Brussels in February 2017. Tom, who organized the Hackfest, presented basically a problem book as prompts for the Hackfest. And one of the problems was, how do we make recordings of information more useful, right? I mean, how many people have hard drives full of recorded RF data that 2 days later you don't remember how you recorded it or how to process it or what it was, and right, you've filled the file name with like frequency and gain and time of day, and right, it's not really especially useful. So how do we make that better? Was the original question. So it is fundamentally just, I'm using the word just here somewhat as a joke, a storage format for digital recordings of analog signals. So at its surface, that sounds very simple, right? You're just more or less streaming data to disk. It turns out it's really, really hard to do this well. And once you do it well, it enables a lot more than you might expect. And that's some of what I want to dive into this talk today. So before I go too much further, right, you have to do the obligatory XKCD specification standard thing. We've already seen it like 4 times this conference already, right? So yes, SigMF is indeed another, call it a specification, not a standard, still applies. I would argue, however, that there was indeed no other solution for what we wanted to do that met our requirements or that was accessible to us. So these were the original design goals. These were the design requirements for SigMF. Maximize speed. So what this means is we want to be able to record data to disk from a radio system as fast as possible. And then we want to be able to read it off the disk as fast as possible. Guarantee portability. So this turns out to be an especially critical point. Guaranteeing portability is more than just you give somebody else a stream of RF samples and they know it's a stream of RF samples and they can use it, right? It means that the way in which you have described that data cannot be interpreted in any other way than what you intended. So we'll talk a little bit more about that. But that's especially important in terms of not wanting to lose understanding, which becomes extremely important for things like machine learning or collaboratively processing data, and you want to annotate things that somebody else understands. Minimizing software requirements. So we would like to be, for anyone who's building SigMF tools, for those tools to be able to run on tiny little embedded systems that don't have a whole lot else going on, right? So we don't want huge dependency chains. We don't want it to be extremely difficult to implement SigMF compliant tooling. The ability to link many time-varying recordings. So this one, we didn't really figure out until probably 2 years later, but I think we've got it now. So I'll give an example of what this means. So imagine you have an airborne receiver. It's a dish mounted on the bottom of a plane, and it's flying around, receiving data, right? What are all of the things that you might care about, other than just the RF data? Well, you care about where the plane is, right? You might care about the direction of the dish. As the plane banks, the dish is going to change, right? You might care about the temperature of your dish. Right? What is the temperature of the dish? So what was that, 4? Just right off the top, right? Depending on what you want to do with that data, understanding how all of those different recordings impact each other matters. And you have to do it in a way such that you know, I'm looking at RF sample 1,000,001, what was the temperature when that sample was taken, right? And those two streams of information were recorded with different sensors. One is a thermometer and one is a radio receiver. This is an interesting problem. So sharing portions of data set without sharing the whole. RF data sets are, we heard Steve Croft from SETI talking earlier, right, about the immense amount of data that their large antenna arrays capture and how to deal with that. Ideally, you don't, have to do what the black hole folks did and ship a suitcase full of hard drives across the world because it's actually the fastest way to get data somewhere. And to be clear, SigMF would not have solved that problem. That was an insane amount of data. But we want to make inroads. So allow for arbitrary metadata. So this could seem at odds with the guaranteeing portability piece of this, right? So we said, OK, we want to be able to describe RF signals with metadata and give it to somebody else. But we also want it to be possible to make up new metadata that no one's ever seen before and for them to know what that means. That's super hard. Facilitating easy integration with existing tools and workflows. I will say that this is a fundamental part of open source, right? Being able to use your existing tools is key. How obnoxious is it when you get some file that you can't grep, right? Or that you can't process with simple command line tools? It fundamentally breaks a lot of open source workflows, and that we wanted to support those. So the metadata must be easily indexable and editable. This becomes especially important if you want to do things like store it in databases and then search through that. The specification must be understandable. I'm not going to call out any other specifications by name. I would argue that this is something that RF specifications just generally kind of pretty terrible at. They are huge PDF documents, usually hundreds of pages long, that make very little sense to anyone else that tries to read them. And we did not want to be that. And we wanted this thing to be governed and maintained as an open source project, right? And this is why all development happens on GitHub, all discussion happens on GitHub, decisions are made on GitHub, and the format of the specification is a lot like an IETF RFC. All right, so going back to the question of why didn't you use any of these other things? Why didn't you use Vita49? Well, the answer is Vita49 is a transport format. It's not a storage format. Yes, I realize there are a lot of people who stream Vita49 to disk. I would argue that once you have done that, it breaks like 8 of these. Also, to quote somebody from the Vita49 committee to whom I talked to about SigMF, you could drive a bus through that standard. That breaks the point of compliance, right? How many people have received a Vita49 recording and then tried to put it through your Vita49 deframer or decoder, and it didn't come out the way you thought it would? Thank you for being the only person to raise your hand, Marcus. Anyways, we actually, we see Vita49 as an important partner, right? SigMF is not a streaming standard. It's not a transport format. SigMF does not care what your data looks like over the wire, right? SigMF cares about what your data looks like at rest. So Vita49 we see as an important partnership. HDF5 is used pretty heavily, especially in the astronautical sciences. NOAA uses it, for example. The problem with HDF5 is it doesn't meet our portability requirements. It describes a way of recording data, but doesn't guarantee the compliance or the understanding, right? That idea of if I give you an HDF5 recording, yes, you could read the data out of it, but you're not necessarily going to know what it means, right? Interestingly, this is the problem that digital RF solves. So digital RF is like, you know what? We're using HDF. Digital RF is run by MIT Haystack. They wanted to use HDF5, but they had that problem. They were like, we want to use HDF5, but nobody knows what any of our data means. So I would argue of all of these, digital RF is closest to SigMF. It actually started 6 months after the SigMF standard was published. In retrospect, I wish that there had been more collaboration between the two. I feel like we probably could have come to an agreement on something that might have solved both problems. But by the time we both got to where we were, we had solved different design goals. Digital RF is probably the closest to SigMF of all of these, though. Pickle is Python specific. It lacks some metadata mechanisms. Midas Blue is designed to be used with Midas. It has dramatically different design goals. Cindy, I apologize for walking back and forth on the stage. Okay, just keeping you on your toes. All right, so to use a bad joke, I couldn't resist. SigMF took off way faster than we anticipated. Way, way, way faster than we anticipated. So we spent 3 days at Tom's Hackfest just debating. All we did was have 3 straight days of design discussion. And then we spent maybe 2 weeks following that, recording that in a way that was mostly understandable to other people. And I think what came out of that was we solved some really hard problems that a lot of people were suffering in a way that was fairly simple. Now if you go read the specification and you see some of the decisions we made, you think, oh, yes, that is kind of the obvious way to do it. That's kind of the goal, for you to read it and think, this is simple, this is obvious, right? In the process of having gone through this and looking at what everyone else has done and the other options that were out there, most people have not done that for different reasons. So I think because of the success of solving those hard problems, adoption really soared. And so we are actually yet to make a stable SigMF release. In fact, for probably close to 18 months, there wasn't a release at all. There were large portions of the specification that said TBD. But adoption took off, even with that. People started using it in their programs. There's significant tooling built around it. And so that was kind of a lesson learned for us in terms of preparing. So I do want to also plug Dana Boquin's talk tomorrow on Metasat. So she's the head librarian at the Harvard-Smithsonian Center for Astrophysics. Has been awarded funding from the Sloan Foundation to work with LibreSpace SatNogs, and they're working on metadata problems. So to give a few other examples of how this has exploded, one of the most active groups in SigMF development is the NTIA. You might have heard Peter Mathis refer to this. I'm sort of waving arbitrarily. Peter! You might have heard Peter refer to this yesterday. The NTIA is deploying sensor networks using SigMF. And thank you, Peter, for actually publishing your SigMF extensions. To date, Peter is one of the only government groups to openly publish their SigMF extensions, which is awesome. Thank you very much. Yes, he deserves a round of applause. To give another example, In-Q-Tel built a multi-sensor system for taking SigMF recordings, kind of going back to that point I made before. And then they built this incredible web framework for navigating those recordings. You can say, okay, what I care about is the video camera that was on this drone at this location at this time, and give me all of the RF data that's relevant to that. They published a paper about that in last year's technical proceedings. So this is the currently available tooling. It might strike you as interesting that given how many people are using it, there's not that much that's public. This has been one of our issues with SigMF, is that the vast majority of adoption and people using it are doing it in silence. So please, 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 I know there's at least a dozen of you that have implemented Vita49 to SigMF converters. Please just give me one of them. Just one of you. Give me, you could dead drop it on a USB drive to me. That's fine. It's fine, I don't care. I bought a Raspberry Pi just to deal with dead drops. Just give it to me, okay? Because there's no way I'm plugging one of those drives into my computer. I have a Raspberry Pi for dead drops. Anyways, these are the 3. So the top is from SkySafe. These are effectively the canonical SigMF blocks. Again, SkySafe is a sponsor. Thank you very much, SkySafe. GR-SigMF is used heavily. DeepSig has released, I'm talking about them in the third person, I work at DeepSig. We have released 2 SigMF tools, LibSigMF and SigMF Recorder. Nathan West, who's sitting over there and pretending like he's not listening, I see you smiling, is the designer and maintainer of these. So things have grown really quickly, and we've learned a lot. And one of the things that we discovered is having solved those simple problems, we now see really interesting new problems that we want to go tackle. The first one is, how can machines automatically understand metadata it's never seen before? Now, I want to clarify, this is different than what I said previously. This is different than, for example, the NTIA, one of their extension namespaces, describes their antenna systems, right? And they can give that, and you can get NTIA's specification for their antenna systems described in SigMF, and go off and do your own tooling around that, right? And you can understand NTIA's SigMF recordings. We want to be able to do this such that it's completely automatic. Like, your machine can get a SigMF recording, realize there's data in it that it doesn't know how to parse or understand at the machine level, go out, grab the information it needs, build it into its own parsing and processing system, and then be able to use it in a meaningful way. And I think we have the foundation to do that. And I again, going to plug Dana. These topics are only possible because Dana is a librarian, and it turns out you need somebody who knows library sciences to tackle these kinds of problems. So we're very, very lucky that Dana got involved. Secondly, how can we describe the observation system in a way that's understandable to machines? So this perhaps sounds a little bit obtuse. I'm going to just try to describe it a little bit more. So let's take the ATA, for example. And you get a SigMF recording from the Allen telescope array. There's 42 dishes. And let's say the array is tracking a satellite pass, right? So you have 42 dishes that are moving as you're recording this data. So, and all of those dishes have a lot of different things going on, right? They're cryogenic, right, apertures. Like what? There's a lot of different types of information there. So that makes sense to a human, and you could, and given the previous example that I said, right, you could say, okay, like I want to know what the information looked like from these dishes given this pass, and like we've solved that problem. But does the machine actually understand what that information means? How can you describe the observational system such that a machine actually understands the experimental setup and how it impacted the data? And this is especially interesting from the perspective of machine learning, right? What if we could teach a machine to understand why data looks like it does? What are the effects of your observational system on that machine? What does a recording mean, to get to meta, right? Like what actually is a recording? If somebody gave you a whole bunch of recordings, could you include metadata such that a machine automatically understood what those recordings were? I kind of think the answer is yes, and I think we have discussions about how to get there. So a lot of people have built SigMF systems. They actually at NTIA's IceHeart conference last year, I happened to mention that we have all these things in the works, right? And I think NTIA got a little scared. We're like, wait. You're gonna break the government systems when you change all of this. I promise you we won't. We have a plan. So SigMF uses semantic versioning. Does this laser pointer work? All right, semantic versioning. So for anyone who's familiar with semantic versioning, the fact that there's no 1 in the first digit means there's never been a stable release. There's actually only ever been one release of SigMF ever, which is 0.0.1. That's what most people are using. So that, in what currently in development, like if you go to the master branch of SigMF, right, it's release 0.0.1, and then all of the changes on top of it. So everything that we've talked about so far in terms of our future vision for where we want SigMF to go, this ability to understand data it's never seen before, right, all of these concepts, we've reached the conclusion that there's no way to do this without breaking backwards compatibility. We believe we have a way to get there, but we have to break compatibility. So here's the plan. We're going to close the issues, merge the PRs, finish the discussion, and make the structure that we have now rock solid for the way everybody is currently using it. We will tag 0.0.2, and then we're going to put that into maintenance mode. There will be no further feature development on that branch within the canonical SigMF repository. We'll fix bugs, et cetera. Hopefully, there are no more typos. But outside of that, we will no longer devote development time to that structure. And from there, we're going to take off on 0.1.0. We will break backwards compatibility, and the goal is to enable the sorts of things that I've been talking about here, which involve new tools, new structures, and I think some really, really cool research into how do you describe not just radio data, which is the problem that we initially set out to solve, but how do you describe radio systems? How do you describe sensor environments? Right? How do you describe those in a way such that you don't have to tell another machine how to understand them? It can learn over them on its own. That's where we're headed. So I usually give a yearly SigMF workshop that's an hour long. I wanted to give this talk in not a workshop form to get a larger audience, because I know a lot of people are currently using SigMF, and I want this to be super, super clear so that everybody knows how this is going to happen. So if you're currently using SigMF, you've already deployed it, release 0.0.2 will be the final feature improvement release in the current structure. And then we're going to break it. So please get involved. I know there's lots of SigMF code out there. Just give it to me. Just give it to me. We need help with internal tooling. If you don't super care about specifications and you want to come write code, cool, we need that too. There's internal tooling we need help with. It's primarily Python and some web tools. We need help with external tooling, right? So those are things like using SigMF in interesting GNU Radio applications. And discussion about the specification itself is invaluable, right? Every time somebody new comments on a SigMF discussion topic, which are GitHub issues, I get really excited because it means somebody really cares. And everybody's perspective matters here. It is an open source specification. So if there's something that you want to be able to accomplish with SigMF, especially in 0.1.0, now is the time to tell us, right? Tell us now. Because the plan is for 0.1.0 for us not to have to break backwards compatibility again in the foreseeable future. Right? We want that to be the enabler for a long time. So with that, ended 4 minutes early, I'm happy to take questions while next speaker gets set up. What's up, Pat? What's up, Kyle?
So, you want mics? Yeah, you can come on. You're using the...
Okay. Oh, here, I can pull them up for you real quick.
Okay, excellent. And please speak into the mic.
All right. Can you reconstitute a signal from SigMF and compare it against the original?
So SigMF is written specifically to record the raw IQ post any like radio pre. I'm using post and pre in a really confusing way, right? So most radios, right, you have your RF front end. It's coming through like an FPGA, for example, that's doing things to it, right? And then you get the data that you would process in GNU Radio, right? The goal is, SigMF is written to take the, what does that mean? Is to take the data post FPGA, pre-GNU Radio processing, right? Because as soon as you start processing that data, information theory says you've lost information, right? So for this to be fully reproducible, we have to capture it at that point. Yeah.
What are the type of breaking changes that are happening with SigMF? And like, can you go into more detail about them and what we should expect with them?
Yeah, the biggest one is, so SigMF is written in, huh? The biggest one is that SigMF is written to be JSON. We are going to move to JSON LD. That's the biggest.
One sec. I'll be right there.
This is probably the last question.
Hi, Ben, I'm Richard. Just curious, can you save the executing flow graph in the metadata of SigMF? Or could there be an extension to SigMF in which you can save the executing flow graph YAML?
Yeah, so we're having part of the discussion about describing an observational system is necessarily the description of, because, right, no SDR system is just hardware, right? The system is hardware and software. So your ability to archive a snapshot of that is a fundamental requirement. So if you imagine, for example, to give a really complicated case, something like RFSOC, right, a Xilinx RFSOC part, and the state of RFSOC when it is recording data, and how many different state variables exist, right, software impacting hardware. If you wanted to completely be able to reproduce that state of RFSOC at any other point, you have to have it captured in a way that's completely, right, archived and represented. Right. So yes, this is the short, long answer. Yeah. Okay. I'm out of time. Thanks.
Thank you, Ben. Round of applause. And